Okay, welcome. Today we have another delicious paradox to explore, Olber's paradox, and talk about the very distant universe. So what's going on here? I am Robert Nemiroff. This is the beautiful downtown studios of Michigan Technological University. And the official course title is Extraordinary Concepts in Physics, but you are welcome if you're just browsing the web or searching through iTunes to tune in. And there's a whole bunch of lectures. I think we're over 30 lectures, little 15-minute lecture snippets by now. We're available on the web in this really small type, but you can search for Starship Asterix and Physics X and find that forum, and you'll see all the lectures listed there sequentially. All right, so let's think about the universe as a whole for a second. There are several ways to consider the universe as a whole. One is called the cosmological principle, and that is where you consider the whole universe to be homogeneous, which is the same everywhere, and isotropic, the same in all directions. It's very simple. It's a very simple model for the universe. It's easily describable in certain mathematics, and that's what general relativity does. So an example of homogeneity is when something is smoothed out. So you could take the room you're in and smooth it out by dissociating all your molecules and that of everything around you until it's uniformly spread throughout the room. One common example given is Jell-O. So Jell-O, if you look at it, seems pretty homogeneous in there. It's because of the way it's made, I guess. Some people put fruit in Jell-O. And not only does it make it taste good, but you would think it makes it chunky, so it's no longer homogeneous, which it is no longer homogeneous. So if your universe is made of Jell-O and it had fruit in there, there would be a problem. But think about the whole container of Jell-O. You could take the fruit in the Jell-O and think about it averaged over the whole container. So if you take the Jell-O and the fruit, then on the size scale much greater than the fruit spacing in the Jell-O, that Jell-O container is homogeneous. Isotropic, as I mentioned before, I like to repeat things. I don't think repeating things is necessarily bad. It helps emphasize what's more important and helps people to think about things possibly in a slightly different way. So isotropic means the same in every direction. So for instance, right now, if you look around, you'll notice that the things on your computer monitor might be different than the things in other directions, unless you have computer monitors everywhere. I don't know what it's like where you are. So if, however, you were to pull the plug and turn out the lights, then everything would be dark. And then it would be the same in all directions. And if you were to get dizzy and turned around and it was completely dark, you wouldn't really know which direction your computer monitor was. So the universe is thought to be the same in all directions, but not necessarily dark, which brings us to the crux of Olber's paradox. Olber was a guy who lived, I think, in the 1600s. I should have looked that up. He asked, why is the sky dark at night? Now, that's something that everybody knows. Every school children knows that the sky is dark at night. Why is this a big deal? Well, Olber was famous for coming up with this question as to why is it dark at night? And everybody would just think, well, of course it is. But of course it is isn't a reason as to why. So Olber said, everybody assumes also, besides assuming the sky is dark at night, that the universe is infinite in all directions. And here's a key assumption. All stars have the same surface brightness. So if you were to take the sun and you were to cover up all but a little piece of it, it would have some kind of brightness. And then if you were to cover up another little piece of it, let's say you were to have a piece of paper and put a hole in it and look toward the sun, supposing the sun wouldn't blind you. It would look the same, that hole would look at the same brightness no matter which part of the sun you put it over. Now let's say that you move the sun twice as far away. You would get 1/4 of the light from the sun. But if you had your little pinhole piece of paper and you looked at the sun through it, and whenever the pinhole was over the sun, you would see the same brightness. You couldn't tell if the sun was 4 times further away, twice as further away, 100 times further away. So long as the pinhole is in front of the sun, it is the same surface brightness. In fact, people used to try to estimate the distances to stars, because they would see the stars at night would have the same surface brightness as the sun, so they would then wonder what surface brightness that was and therefore how bright that was and try to use that to figure out how far away they were. The problem is people didn't know the atmosphere smears out the brightness of the stars, but still you can get some estimates that way. Surface brightness, it turns out, as Olber was correct, does not depend on the distance to an object. So Olber said, let's point in any direction. Point there, or point in this direction, or that direction, or this direction, or surprise, this direction. Any direction you point to, Olber said, should go through empty space, first and foremost, but if the universe is infinite, should end on a star. So this star should have the same surface brightness as the sun, assuming, or something close. Cut him a break, something close to the sun. Yeah, the sun's not the average star. Well, it's the average in some ways, but many stars have a little bit lower surface brightness, some have a little bit higher surface brightness than the sun, but it's about the same. Still, though, if you point in any direction, you should end up on a star, which means that the sky should be really, really bright. At night, even. But it's not. What's going on? And it's such a fundamental paradox, and it makes people rethink some fundamental concepts that it became quite famous. Okay, so here's a drawing, different than the one I made. So you are here at Universe Central, and you spin around and you point your finger, your arm, in some direction, and no matter which direction you point to, if the universe is infinite, we'll end on a star, and the sky should be bright. So what's going on? Oh, here's another analogy. We now pause for another analogy. Let's say something even more close to your own experience. Let's say you go into a dense forest, and don't pretend this hasn't happened. Trees are found in every direction. Every direction you point to, therefore, ends at a tree. So if you're in a dense enough forest, you're going to see brown in every direction. That's the way it works. Actually, how much sunlight comes through the treetops is important as to how dark the brown is. There's no analogy in that in Olber's paradox, so we'll forget about that for now. So what is the solution to Olber's paradox? And people have suggested solutions throughout the ages, ever since Olber suggested this. Is it that the universe is actually finite in size? It only goes out a little ways, maybe a long ways, but not so far. Maybe the universe is finite in age. Maybe it's not all that old. Maybe there's all this dust that blocks out most of the light. If you look down through the Earth, there's one big chunk of dust there that's blocking out the starlight. Maybe there's other chunks of dust elsewhere. Or maybe the light just gets too redshifted to see. Which is that? So you can whistle Jeopardy music to yourself while thinking about this, and then magically jump into the future by pausing the frame. Okay, so here's what you do. Pause the frame, whisper Jeopardy music to yourself, think about it for a while. Talk to your friends, call your neighbors, see what they think, and then unfreeze it right now. Welcome back. Did you have a nice snack? Good. Okay, all of these things affect the brightness of the night sky that I mentioned before. And if you forgot what those were, here they are. Finite in age, finite in size, dust blocks most of the light, light gets too redshifted to see. I'll discuss redshift soon. Well, another lecture. But the finite age of the universe turns out to be the most important factor. It turns out that light just can't get to us from distant stars because light just doesn't have had time to get to us. So when you look in a mirror, you see yourself, but you don't see yourself as you are right then. You see yourself as you were a fraction of a second ago. You see yourself as light bounced off of you and bounced off the mirror and then came to your eye. So it took, since light has a finite speed, that it takes a finite amount of time for that to happen. So by the time you see yourself, you could already be dead. If you move the mirror further away, you're seeing yourself further and further in the past. But then, bag this whole mirror thing, you see your friends and family as they were in the past. So if your friend stands across the room from you, light leaves them, takes a finite amount of time to get to you, so you only see them as they were in the past. They could have run away and not be your friend anymore. If you see a star, for instance the sun, it might not be there anymore. It takes the light about 8 light minutes to get here from the sun. And when that happens, so that the sun could have been gone about 8 minutes ago, 7 minutes ago or so. It could be gone. We wouldn't know it. Now the distant stars, as you go further out, we see them further and further back in time. Eventually, you get to back where the universe started. We can only see back a certain amount of time. Turns out it's 13.7 billion years. Before 13.7 billion years, the universe didn't exist. So even though the universe could be infinite in extent, light from those stars had not had time to get to us yet. There are also those stars way back out there who didn't even have time to form. I mean, they're formed in our current time, but we don't have the time to see them as they are. So as your friends move further and further away, you see them when they were younger and younger. So ultimately, if someone announces that they're 100 years, light years away, and you see them, you're seeing them as they existed 100 years ago. So they might be a baby and you could be 100 years old. Okay. So that's the solution. It took people a lot of time to debate this. It's a really cool paradox. It turns out, though, with very modern information, that Olber was sort of, the question was interesting from another point of view because the sky is bright at night. It's just that our eyes adapt to the tremendously bright sunlight of our sun. And so we're not able to easily see the brightness that exists there. The night sky glows at every color imaginable, all the way, not past what we can see, all the way from the radio to the gamma rays. The night sky glows and the day sky goes in every wavelength band you could guess. So Olber was correct. It was a profound question that has a flipped answer. So there are background radiations all across the electromagnetic spectrum. Possibly the most useful one is those in microwaves, which have other uses than heating coffee. It turns out the very early universe was filled with radiation that was bouncing around between electrons, and soon after the Big Bang, which we will get to in a soon lecture, which might already be archived, when the universe cooled enough, photons flew free and eventually reached us. And even though they left when they were gamma rays, they got to us because they were redshifted in the radio band, in the microwave band, and it's called the microwave background. So any direction you look, you would find microwaves. Now you could hold your coffee cup up, and it would not be heated up by these microwaves to any significant amount because it's very dim, but they're there. And studying them actually turned out to be really important. Okay, so this is slightly into the infrared, also taken by the Kobe satellite. So these things, the Earth actually blocks microwaves from traveling too far, and infrared waves from traveling too far. So here you see actually the center of our galaxy here, and the universe is lit up even in infrared light. Okay, so let's now go to the near infrared. And so here are holes where there are no surveys. Let's go to blue so it's more easy to see. But there's lots of stuff here in infrared light that's the background in infrared light all over. So it's true invisible light as well, but we're going to jump to the X-ray light. The X-ray in background is interesting because for a while it wasn't known what was causing it. So here you look in any direction, and it's not uniform because our own galaxy has another effect here, it has an effect here that's somewhat local to our part of the galaxy. And, but if you look in any direction, you will see X-rays. So the sky is bright in X-rays. And the last one with the, this is determined by the earlier, but this map is from the ROSAT satellite. And the last satellite is a currently flying gamma ray satellite, which is the photons of such high energy they will go through your bones and cannot be used to do X-rays. They're gamma rays. They're more blue than your eye can see. And in any direction you look, let's make this red again, you will find gamma rays. So Olber was right. The sky is dark at night, but it's dark to our eyes. The sky is also bright in every direction. And the answers, to understand the answers, we have to understand cosmology and the Big Bang. And we'll be getting to that in future lectures. So I will see you then. Bye.